Thank you very much. Thank you for the introduction. It's a pleasure to be here and to have the ability to talk about AI in healthcare. Life goal of mine almost. It's been now total 15 years I'm pursuing this. A little bit about my background. I'm currently working for H2O.ai, a company that brings machine learning for every application. We have a few different products. You can talk to me about that separately. But I'm here to talk about AI in healthcare. So the relevant experience I have for that is I have worked in R&D and diagnostics workflows through my genomics and molecular biology experience. I have experience in personalized medicine workflows, and this is primarily work I did at the National Institute of Health in the US. Clinical decision support, clinical genomic support. This is again something I did at NYU Langone Health, as well as in collaboration with Cloudera and Fast Forward Labs. And finally, patient-centered systems. I have experience on this type of unification of a data set through collaborating with the PCORNet network, again in the US. So I like definitions. So I wanted to start with a definition of what is clinical decision support, and it is, this is my attempt to it. It's a patient-focused computerized alerts, reminders, and clinical guidelines that aim to improve health outcomes and enhance as well the workflows within healthcare systems. So with the implementation of EHR, electronic health records or electronic medical records over the past decade, in essence, perhaps a little longer, we actually have a lot of CDS, clinical decision support functionality already implemented. And this is just a plot from the George Washington University. It's based on a survey, how the different physicians are using electronic health records. And you can see here clear clinical decision support tools implemented already, being useful. So we have alerts, we have reminders, and various other things, identified need for lab tests. So these are all fall within the category of clinical decision support, but now we're talking about something different. We are talking about more advanced clinical decision support, AI-supported systems within AHR. So until recently, AHR adoption has been a big discussion topic. This is one I mentioned in my title, Roadblocks and Opportunities. This used to be a roadblock for many countries, some being more advanced than others in implementing EHRs. But currently, actually, for all of North America, Northern Europe, some Eastern Europe countries, these are actually reaching now 100%. So there is definitely opportunity, there is definitely the data there for us to take advantage. And not only that, together with the increase in data, and this has happened roughly in the past 10 years, we also have a huge increase in research and patents using AI for healthcare solutions, mainly predicting disease, but also different workflow solutions. And you can see, first of all, there is a lot of opportunity, but also you can see a way I like to read this plot is that the algorithms for healthcare work. We can predict disease, we can. Now it's a matter of implementing it and scaling it and refining these models as a clinical decision support tool. And here, allow me to make a small parenthesis to mention why I say clinical decision support. It's very important to understand that I'm not proposing to have standalone AI systems in the hospitals. As a recent experience with FDA approvals and research related to FDA approvals of image diagnostics using AI, the best results seem to happen in healthcare when we have a joint decision making. So we have AI to suggest an alert or to suggest something that where the physician needs to pay attention to, and then the physician at the end will have the final word. And this is what I'm suggesting right now to avoid misunderstandings. So even though the opportunity is definitely there and a lot of the roadblocks have been lifted, the rest of the world that's not yet there, it seems to be accelerating towards reaching there. There's still some challenges and mainly have to do with data governance and technical and operational readiness. Different countries, since I come from the US and I thought an international plot would be useful to have here. So these are like the top quadrant countries, and these are historically the countries where also most AI in healthcare research has been coming out for good reason, as you see. So technical and operational readiness refers mostly to software and hardware, and when we talk about data governance, it's mainly the ability of different providers to talk, the data from different providers to talk to each other, not be in silos, communicate, be in the standard format, and there's still quite a lot of problems in that area. I know definitely in the US, but also in other countries, this has to do a little bit with the legal framework of healthcare and how fragmented the system is, or how centralized it is, but it's not a one-to-one correlation. So I just want to move, having given a little bit of the background, I want to move straight and give you the 3 examples I promised in my abstract. 3 examples of EHR-based intelligence CDS, and intelligent goes for AI, of course. So first of all, this is referring to a published research work with the NYU School of Medicine and NYU Hospital, Langone Hospital. It just got published last spring, and our goal for this work was to predict obesity in children. As many of you might know, obesity is a huge epidemic in the US and globally, now affecting more than 30% of the total US population, and unfortunately, in some cases, more than 25% of also children population. So a little bit of what we embarked to do, we wanted to predict obesity at 5 years old by having records from birth until 2 years old. And this is important because previous research has shown that this period between 5 and 7 years old is critical in order to cure obesity or prevent obesity. If the child at that age is obese, the chances of being an obese adult quadruple almost. So that's why we focused on that, and also this by using these early years in the life of the child, we take advantage of this network we actually had, the data from the network we had, where we have 8 primary care and over 40 school-based clinics in Brooklyn. So this meant not only we have a quite big data set, but also we were able to obtain linked EHRs from the mothers, because we have both the schools and the primary cares. These are facilities that are primarily serve the community, so we're able to have this linked information. We have 8 years of records, and yet almost a little more than 35,000 children with mothers. So this is something that we were very happy to see that it works very well. I'm not going to go into the details of the model. This is actually a GLM with L1 regularization. We did separately boys and girls because there is historical research reasons to believe that, to think that different factors might affect. What I want to draw your attention is, unfortunately, this highlight got moved in the process of saving. Actually, what I meant to highlight is in the prediction for girls, which is actually a better prediction, maternal post-pregnancy weight, and this is where that linked information I mentioned comes in, is actually the number 1 feature in terms of importance. And here are the feature weights on the side for comparison reasons. So it's the top 1 feature for girls is not even present for boys, but what's important is we start seeing those here, and as we believe that as more and more records will be linked, historical family information will be available, so we can actually address more and more preventative healthcare issues, like in this case for obesity. A second case I want to talk about is experience we have at H2O. Comes from experience we have at H2O. This is an application where EHR from intensive care unit data over 4 decades of those and the right infrastructure of the provider were able to help and implement AI as a clinical decision support. So what we know about ICU from research is patients that have an unplanned transfer to ICU actually have much higher mortality rates and much longer stay in ICU. You can see here some statistics. These come from the US. The cost is quite significant. ICUs are heavily used, which also means not only the need for their optimization is big, but also data can be easily acquired in most cases. So this is an example where H2O AI and Kaiser Permanente were able to devise and deploy the advanced alert monitoring system. Kaiser Permanente is using 40 years of data, is one of the very early forces of IT in healthcare. They started efforts of digitalize since the 70s, so that's pretty wonderful. And we have typically HR data, chemistry, vital signs, demographics, comorbidities, and here bed transfer, like internal hospital documents of how the patient was moved between the different wards. And the goal was, in essence, to predict which surgery patients will fatally deteriorate or eventually be transferred to ICU. And there were 4 steps. First is risk analysis, which is building the model, training. Then it's monitoring and warning, deployment. Then we have disseminations and communication and intervention, which is now where the physicians, the trained personnel comes in to act on the alert that the clinical decision support system is bringing. So this is a diagram of how it works, and it's currently deployed, and they're always looking to upgrade and improve the system. So for every patient, their vital signs and all the information is being monitored. When at some point the patient, so in the red line, we can see the expected course of health deterioration for the patient. So he's relatively stable, then it starts deteriorating, and after a certain point, there is a point of no return. So AAM triggers exactly at the right point where the physicians need to pay attention and the interventions have maximized effect. And finally, I want to talk a little bit about the potential of explainability in clinical decision support. For a more extensive talk, please go after lunch to Bahador's talk on explainable neural networks. What I'm going to mention here is that it's very, very important to think about explainability in the context of clinical decision support, in the context of AI, of healthcare applications of AI. And this is, first of all, because it facilitates adoption. This is a science that has been, probably it's the oldest science out there. And there is a lot wrong tradition and a lot of evidence on which the current procedures are based. So allowing the physicians to see the algorithms under the lens of the type of variables they're used to knowing and understanding, I think this makes a big difference. And in my work at NYU Hospital, this was a big focus, usability by physicians. Then, of course, helps put the model in the context of what's known in medicine. That's more like global codes, codes that describe the model as a complete, like high-level workflow. But then if we start thinking about personalized medicine and we want to start getting to the personal, then we have also the local explainability algorithms that give you exactly the reason codes for a specific patient to be in a high-risk zone. And this is the type of example I just want to give. I'm going to talk about sepsis, and in ICU, this is not the Kaiser Permanente example. This is actually a data set from Kaggle. I can give you the link if you want to play around with it. It's pretty fun. So what I did here is having the data from ICU and labels on whether the patient developed or did not develop sepsis, I wanted to see if I can predict sepsis 6 hours before it's actually typically reported by the physician or the nurse. The data set contain typical ICU information, demographics, as well as some clinical lab tests, as well as monitoring, bedside monitoring, heart rate, respiration, and all these things. And what would be the operational advantage by having such an algorithm, such a model deployed is, of course, improve patient outcomes and reduce length of ICU stay and improve turnaround and associated costs. So the model trained pretty reasonably, ROC area under the curve 0.93, precision recall area under the curve 0.76. And again, what is very important with clinical decision support, there is always, of course, going to be false negatives, and these are very dangerous in healthcare, but I'm talking about high-risk individuals. So this can be all incorporated into the outcome. So what is very important, okay, we have a pretty decently trained model, at least. So what can we do with that? So here I show you Shapley values from 8 random inputs, and literally I just went to a random row ID and just extracted this data because we have, I think this data set has around 50,000 rows. I wanted to show something that would be explanatory enough. So by random inputs, I mean 8 different individuals recorded in that data set, right? So what we see here is the contribution of age and hospital admission time, which means how long before admission in the ICU the person was admitted in the hospital, longer or very soon before he or she got into ICU. And here I present the Shapley values. This is one metric of, for local interpretability. It's something we actually like a lot at H2O.ai because it has sound mathematical background and very good mathematical properties. For example, if you sum up all the Shapley values, you will get the outcome of the prediction, whether it's regression or probability of classification. And so it's additive and also it's signed. So it tells you if it's a positive contribution or a negative contribution to the outcome. So you see here that the age of the patient consistently has a positive contribution, which is like if you can put yourselves in the shoes of a physician, this is very reassuring because yes, we know that the older the patient, the more in danger of something going wrong in ICU. So this, but also notice that all these Shapley are not the same. And here we have a hospital admission time that really changes from patient to patient. For some patients, having been admitted and having spent some time to the hospital seems to be helping their ICU sepsis outcomes, but for others seems to be actually a negative factor. So imagine this for factors like systolic blood pressure, if they come up, allowing the doctor to understand. And of course, I don't mean by that correlation is causation. Much more experimenting and experience is known to go to causation from a completely unknown feature seen in the model, but we already have knowledge through previous research of which features are actually causal. For example, in this case would be age. We know it's causal. The organism cannot perform as robustly. So it could be used like that. I want to thank you all for being here. And I also want to thank Ben Busby at the NIH, Dan Trahina, Narges Rajavian, David Mordecai, Samantha, and Brian at NYU. And of course, it's very hard to pick out a specific person in H2O.ai. We're a very tight-knit team. I do want to mention Patrick Hall, and thank you, everyone. That's all.
Hi.
Hi.
So you said that this, so you had like 4 decades of data for this?
Kaiser, yes.
Right. So in 4 decades, there's been like a lot of changes, right? And when it comes to like the technology on how hospitals and how doctors treat patients, like how did you take that into consideration when you were building the model? Or
Yes, this was a big project involving stakeholders from all sides. So there were data scientists, physicians, there was a great collaboration, an exemplary collaboration between data scientists and physicians. So all these factors have been taken into account. These were all, it was more of a collaborative project. The goal of it was not AI to replace physicians, so that's how they started from the beginning. I do understand when you say, when mentioning that, you know, protocols change, strategies change. So these were addressed. There are ways to address these issues by subsetting the data, segmenting based on periods, and checking for consistencies, and also figuring out if there is a specific, like, different distribution for certain types of data than others in regards to outcome. But yeah, these were all taken into account. And there is quite a lot of examples that I am familiar with, not necessarily the Kaiser Permanente, and exactly on the basis of what you're mentioning. There is also care that needs to be given when you're using data, patient data, from procedures that have been administered in various different locations. There is a bias, like if you want, a batch effect from location to location, and many companies actually have seen that this roadblock. One way to avoid the roadblock is to agree that my data are specific to this facility, or to enrich your data, and that's what many people are doing, either purchasing or through collaborations. They try to enrich their data sets with multiple sources of data.
Okay.
Does this answer?
Yeah, thank you.
Great, thank you.
I have a question about modern situation which emerged with big data and new machine learning algorithms, because what you discussed is very similar on old statistical models which exist like 30 years already. So what is new actually in the last maybe 5 years?
Okay, so I feel this is not healthcare specific. It's a very interesting discussion actually. Coming from a background of academia, I have heard both arguments, you know, statistics is the best, hypothesis testing, or model building in classical or data science. I don't see a fight there. I actually would like to see both methods working together, and there is a special, and I don't agree with you that what I presented is primarily classical statistics, because when you're bringing in proxies, when you're bringing in thousands of features and you're using information technology metrics to understand how well your algorithm is performing, that's, I feel, beyond. There is always statistics in data science, but it's a little one step further from that. It's using all the hardcore data science techniques, if you allow me this term. But specifically for healthcare, actually, it's a very interesting discussion, because I actually think this is the one field, perhaps it's because I care so much, that the two need to work together. The physicians can definitely benefit from what AI has to offer in the bedside, and that's specific. There are many more applications, but now we're talking about the bedside. But they will not take advantage of this opportunity if we don't start talking the language of science and giving them some proof, for example, about causalities, if we want to get there, giving them some long-term projections that have some statistical foundation for being believed. And I think this is where the data science community has been a little strict, if you want, and not actually allowing for this plurality of methods to work for the betterment of healthcare.
Following up question, this is algorithm sort of new, applied to old problems, but as we know, healthcare very strict about proof of working specific methods. So if you introduce some machine learning algorithm, it should be statistics from clinical research that this method actually applicable to these specific patients, these specific demographics.
Yeah. So there are two ways I see this question. One is in terms of what you're trying to do. I am if I want to have an algorithm that is claiming to, on their own, save lives, first of all, it needs FDA approval in the US. And it needs, in order to be adopted, it needs all the, and even get the FDA approval, it needs all the research, the papers, the proof of concept, right? It needs all the, but I'm not talking about complete takeover about AI. What I'm saying, and there are already alerts, for example, within EHR systems in the US and in other countries. What I'm talking about is an alert of highlighting high-risk patients, and then the standard processes can be applied for them. There is no, if we have 13,000, 14,000 ICU patients in the whole of the US, but if you have, I don't know, in a night, if you have 30, 50, 100 patients coming in ICU, wouldn't it be more efficient and even more beneficial for the patient if you could allocate resources in order of, with the order of emergency and need to address these people? This is what we're talking about. Now, when we go into explainability, that's a different, this is an add-on. First of all, it's not like the core proposal, if you want. It's an add-on. There is more discussion that I'm more than happy to have on explainability in medicine. But there, I would love to start talking, and many people are doing already, about how do you bring all, first of all, how do you bring hypothesis testing inside the world of machine learning, because using proxies, using these huge data sets that machine learning allows us, also brings the opportunity for hypothesis generation. And that's how I always saw it. Okay, sure, the fact that a feature has a very high importance or a Shapley value, negative or positive, Shapley's actually give us the direction as well, but it doesn't mean that it actually, if I change that variable, it's going to benefit the patient. No way, it doesn't. But we can start imagining easy experiments that can be happen with the same data set to quickly, once something like that is identified, to be tested. And we can also think of ways to automate. But I don't want to imagine too much, because now we go completely science fiction. But this is within the realm of what we can do. That's how I see it.
Thank you for a very nice presentation. With precision medicine or predictive medicine, people are talking about genomics as the next thing. So genomics is becoming cheaper, well adapted. So we have methodology in different use cases are there, like cancer, mutation predictions, or antibiotic resistance, so on and so forth. All these will impact healthcare. So what are your thoughts on these genomics and deep learning, prediction through deep learning, because we know there are lots of rule-based predictions doesn't work well with the current genomics platforms. So what are your thoughts on deep learning or machine learning applied on genomics, which will help in the clinical decision making?
Yes, with exclamation mark, yes. There is definitely a lot of promise. One thing that has personally disappointed me, because I do come from personalized medicine, if you want applications, is how slow actually the field of genomics works in terms of giving us the features, giving us the data that we can use in machine learning. The problem with genomics is we have an immense feature space. We don't have enough people to test the feature space on. So there is now very talented and bioinformaticians. This was my past life. You know, they're working on actually methods to reduce systematically this feature space for cases specifically for cancer, even though cancer might not be the best example, because there's so many different cancers, you cannot say specifically for cancer, but you know, disease-specific set of candidate features in terms of genome. And we do have examples where this works. I know only recently one of our collaborators, one of our customers in H2O is working with Cambridge University in Massachusetts. Given a panel of genes, they can predict cancer. And I'm not going to say too much because it's up for publication. So these initiatives exist. I feel that the reason we don't see them in the clinic is that it's still research papers. You know, we're trying to reduce the feature space in a way that is to reduce the feature space, but not reduce it too much that we lose information. So we are there to try to understand. And also there is all these interactions in the genome that make things more complicated in order to identify the right targets. And I think that's where we are. I think there is definitely a matter of time. But I don't want to finish on that on an optimistic note necessarily, because I have been like very impatient to try to see the field happening. And the last thing I read only this summer, it's this concept of more and more of actually now there is no way to eliminate, to reduce the feature space, because now we're talking a pangenic effect to the outcome. And I don't know how data science can tackle if that is true. Thank you.